Hello everyone, welcome back to week 2, lecture 2. In this lecture, we'll continue our discussion in elasticity. Again, we'll continue to learn the basic concept and the terminology of the elasticity. And we want to provide enough background to the linear elastic fracture mechanics, which will be covered in the lecture number 3 and 4. So elasticity, as we talk about, elasticity is recoverable deformation when unloading. During that time is elastic behavior. So many materials are linear elastic at the very small strain. As you can see, typically strain is smaller than the 0.2% or 0.002, the strain. Again, the strain is no units because it's the length delta L over the regional length. As shown here, most material has very small strain. And as we have been showing the Young's modulus for the virus material, as you can see, the metal has increased drastically. And the rubber has very small modulus. It means the rubber has a lower ability to resist the deformation compared to the metal. Another term, it's very important, it's called Poisson's ratio. Poisson's ratio is to describe the deformation of the material in direction perpendicular to the loading direction. In general, we use mu, Greek letter mu, to describe Poisson's ratio. By definition, mu equal to d epsilon transverse over d epsilon uniaxial or axial stress. For instance, if we're looking at in compression, if I try to compress the material, I would expecting the material will compress in loading direction. However, it will expand in transverse or in perpendicular direction. So the ratio of the expansion in the transverse direction to the ratio of the reduction or compression in the loading direction is what we call Poisson's ratio. Poisson's ratio is another very important concept. That's to show the deformation of the material, again, in direction perpendicular to the loading direction. So in Poisson's ratio, for most material, it's ranging from 0.0 to 0.5. It depends on the material property. For instance, rubber is typically on the higher end, and the more stiffer material tends to go to the lower end. So for isotropic material, all the property would be same in all the direction. For instance, the Young's modulus, E, and the Poisson's ratio are all the same in all directions. For anisotropic material, the properties such as modulus and Poisson's ratio are different in all different directions. For instance, the composites, if I have a fiber and a polymer loading alignment in a different direction, the material would be very anisotropical. Other than Poisson's ratio, another expansion, it's very important in the material property we need to consider. It's called a thermal expansion. Most material will undergo a large temperature change during the service life. That temperature change will induce the thermal strain, the deformation caused by temperature change. That's what we call the thermal strain. The thermal strain, epsilon T, equal to alpha. Alpha is coefficient of the thermal expansion times delta T. Coefficient of thermal expansion is a material property. It means it depends on a different material. So a higher thermal conductivity material, such as metal, will have a higher coefficient of the thermal expansion. On the other hand, for the material has a lower thermal conductivity, such as polymer, will have lower coefficient of the thermal expansion. Alpha is to describe the material response to the temperature change. So as been showing here, if I have a material, temperature change in this case will be increase the delta T over 0. So temperature increase from the lower temperature to the higher temperature. In most cases, the material will expand. So therefore, I have the deformation of the material in all the directions should be equal to alpha times delta T. As such, when we consider the shear strain, we need to consider two parts. The first part is from mechanical loading, or from uniaxial tensile stress, and plus thermal loading. So therefore, in this case, the strain induced in x direction should equal to 1 over modulus the stress in x direction minus Poisson's ratio times the stress in z direction plus the stress at y direction, and plus the thermal induced strain, which is alpha times delta T. The similar general approach can apply to y-axis and the z-axis. Similarly, the shear stress should be equal to xy over 1 over g. G again is shear modulus times tau xy. So the shear strain, gamma, that can be different in the different direction. It depends on the stress applied in different direction. Here, the shear modulus have a relationship with linear modulus or Young's modulus. So shear modulus equal to Young's modulus divided by 2 times 1 plus Poisson's ratio. Now I would like to bring up your attention to one behavior called nonlinear elasticity. In this case, we can expect different materials have a different behavior. So therefore, their stress strain curve will look very differently. For instance, on the left, as we can see, the low carbon steel has very typical linear behavior at the small strain area. And then going into the plastic behavior, so as you can see, it reached to ultimate stress, and then will reach to the fracture. On the other hand, for a soft material, such as the silk, we can expect a nonlinear behavior even in the elastic region. It's very interesting to study the spider webs or the silk, as they actually have very high stress. Concrete, on the other hand, it's very complicated material. It's a composites including water, cement, large aggregates, fine aggregates, and part of air. So therefore, the stress strain behavior of the concrete is very different than the steel or polymer, as you can expect. So the figure here has been showing a very typical behavior of the concrete. Couple of things we can notice. The first, concrete has very minimal tension stress. As you can see, the ultimate or maximum tensile strength of the concrete is very small. On the other hand, we can see the peak compression strength compared to the tension strength can be the order of the magnitude is different. And another thing is the concrete has more fracture behavior. As you can see, the string has very small deformation. Right. In general, concrete will have a very, very small deformation. String at the maximum stress is typically smaller than the 30 microstring. So it's very difficult to determine the Young's modulus of the concrete. The general rule of the thumb in the industry, we do that called the secant modulus. So we use the word secant modulus to replace Young's modulus of the concrete. Secant modulus is the concrete as a 40% of ultimate stress. So you took, this is the ultimate stress, 40% of that ultimate stress, and corresponding to the string. That's what we call secant modulus. That's what we typically use to design the concrete property. Why? Because the concrete can reach to the peak compression strength very quickly with very small deformation. Again, we will spend more time to discuss the concrete behavior when we discuss the concrete mechanical performance. And also, it's important to notice the concrete have many pre-existing cracks during the curing process. We call it the early age shrinkage crack. That's an intrinsic property. That will lead the concrete more brittle than many other materials. So therefore, it's important to discuss this linear fracture mechanics. In summary, in this lecture, we have discussed a couple of important concepts. We talk about Poisson's ratio, which is the property to describe the deformation of the material in direction perpendicular to the direction of loading. And then we talk about thermal expansion, how the material's behavior responding to the temperature change. And then we described the generalized Hooke's law that has to consider the mechanical loading and the thermal loading of the material or structure during the service life. We spent a fair amount of time to discuss the elasticity versus plasticity. Again, elasticity is to describe the material property which the deformation can be recoverable when it's not loading. On plastic, it means permanent deformation will be generated even there's no loading condition. And then we talk about stress and the strain, or strength, stress, and the stiffness of the concrete, again, which is very different than many other materials. Thanks for your attention for this class. And next class, we want to spend the time talk about linear elastic fracture mechanics.